In this lab, we will continue with applying machine learning methods on the dataset of housing from California. So in step 1, we read the data from the file, and in step 2, we explored data analysis. We plotted interactive box plot for each of the variables in the dataset using Plotly. Then we plotted a histogram for each of the variable to see the distributions. Then we visualized the relationship between the geospatial attributes, that is longitude and latitude, with the median house price using Folium. Then we identified all the missing values in the data. We filled them using an imputer from sklearn, then double-checked if we still have those missing values. Then in step 3, we performed feature engineering. We created 3 new variables: average rooms per household, average bedrooms per room, average population per household. We encoded the categorical variable ocean proximity using one-hot encoder. We used the library from sklearn to split our data set into training and test set. Then we performed a standard scalar and a robust scalar on both XTrain and XTest dataset. Then in step 4, we are developing regression models. Regression models are relatively easy to implement, given that we have done all the preparation steps: encoding, scaling, and etc. In task 9, we will implement 3 different regression models. In this lab, we will implement the linear regression model. We will try our best to find the best parameters for these models using RandomizedSearchCV and GridSearchCV to make sure that they have their best accuracy. We will evaluate these models using root mean squared error and mean absolute error as the criteria. We will plot a comparison between these models in the very end. We are free to use sklearn and XGBoost or any other packages that we want. So first, let's create linear regression model. From sklearn.model_selection, we will import RandomizedSearchCV. From sklearn.linear_model, we will import linear regression. To find the optimal parameters, let linear random CV equal RandomizedCV of bracket linear regression, open and close bracket, comma, curly braces, fit underscore intercept is false and true, copy underscore x is false and true, n underscore jobs is -2, -1, 1, positive is false and true, close the curly braces, cross validation equal 5 and n iteration equal 2. So we have linear regression model formed. We fit the model on standard scalar, feature inputs. Let linear random CV dot fit of x standard scalar train set, comma, y train. Then we look at the best estimator and the best score. Get the complete details of the best model. Linear random CV dot best underscore estimator underscore gives linear regression model copy underscore x equal 1, fit underscore intercept equal 1, n underscore jobs equal -2, positive equals 0. Let's do this again. Best score. So the best estimator is linear regression of fit underscore intercept equal false, n underscore jobs equal -1. Best score according to the metric we passed in refit, linear random CV dot best underscore score underscore is -2.5607 and so on. Then we find the optimal hyperparameters. Let's create a function. So instead of repeating these steps for randomized, for robust scale data set, we define a function and we will call the function on different data sets. To find the optimal hyperparameters, we create the definition find underscore linear underscore model underscore randomized of train data. The input is the train data set. We define the classifier let linear random CV equal randomized search CV bracket linear regression open and close bracket comma Kelly braces. So we form a dictionary over here. Fit underscore intercept is false and true. Copy underscore x is false and true. N underscore jobs is -2 -1 1. Positive is false and true. Close the Kelly braces, comma cross validation equal 5, comma n underscore iteration equal 2. Close the bracket. Fit the model on scalar feature inputs linear random CV dot fit of the train set. Then we get the complete details of the model. Print best linear model is the linear random CV dot best underscore estimator underscore best score according to the metric we passed in refit. Print linear model best score is linear underscore random CV dot best underscore score underscore retain linear random CV. We find the best linear model parameters on standardized values. Let linear random CV SS equal find underscore linear underscore model underscore randomized of the standard scalar train set. And we get best linear model is linear regression of copy underscore x equal false and n underscore jobs equal 1. Linear model best score is 0.6515 and so on. Then we find the best linear model parameters in robust scalar standardized values. Let linear random CV RS equal find underscore linear underscore model underscore randomized of XRS, the robust scalar data set. Then we get best linear model is linear regression of fit underscore intercept equal false, comma end underscore jobs equal 1. Linear model best score is 0.6516 and so on. Linear random CV SS dot best score so this is best score is 0.6515 and so on. We already have this displayed, so we don't need to display it again. Next, we will perform GridSearchCV based on the best hyperparameter values from randomized search CV to see if we can get better score. So let's create a parameter grid. Let from grid equal Kelly braces. So Kelly braces mean forming a dictionary. parameters used by a linear regression. Let the fit underscore intercept is linear random CV ss dot best underscore prums underscore and then fit underscore intercept. So here we are finding the parameter grade for the best creating a parameter grid for the standard scalar best model parameters. Let the copy underscore x is linear random CV standard scalar dot best underscore prums underscore of copy underscore x. N underscore jobs is linear random CV dot best underscore prums underscore of n underscore jobs. Positive is linear random CV standard scalar dot best underscore prums underscore of positive. Close the curly braces, print prum grade, and we get fit underscore intercept is true, copy underscore x is false, n underscore jobs is -1, and positive is false. So next we will perform GridSearchCV based on the best hyperparameters from RandomizedSearchCV to see if we can get better score. Function to create a prum grade. So we have instead of creating the prum grade for separate standard scalar and robust scalar, let's write a function. So let's put this over here, just copy and paste. So prum grade equal parameters used by linear regression. So we input the linear random CV, and we from the best parameters we find fit intercept, and we find from the best parameters we find copy underscore x, and from the best parameters we find n underscore jobs, and from the best parameters we find positive. Then we print the prum grid and we retain prum grid. So call linear model prum grid on best linear model. So let prum grid ss equal linear model underscore prum grid. So let's run this underscore prum grid of linear random CV underscore ss, and we get the best model parameters are fit underscore intercept is true, copy underscore x is false, n underscore jobs is 1, positive is false. And we have so we can see that 1 times 1 times 1 times 1 is 1. So we will have one model. So times 1 times 1 times 1. equal 1 model. To apply GridSearchCV on to get the best hyperparameters. Call linear model parameter grid on best linear model for the robust scalar data. So let param grid RS equal linear model param grid of linear random CV underscore RSS. Let's run this and we get fit underscore intercept is false, copy underscore x is true, and underscore jobs is 1, and positive is false. So we get 1 model. So 1 times 1 times 1 times 1 equal 1 model to apply GridSearchCV on to get the best hyperparameters. So from sklearn.model underscore selection, we import GridSearchCV. Then we find the optimal hyperparameters from GridSearchCV. Let's define the classifier. Let linear grid CV equal GridSearchCV of linear regression opening close bracket, comma param underscore grid equal param underscore grid underscore SS, comma cross validation equal 5. So we are this example in this cell we are showing the example of creating of finding optimal parameters from GridSearchCV for the best parameters from the standard scalar model. Then we fit the best model from GridSearchCV. So linear grid CV dot fit of x the standard scalar train set. Let's get the complete details of the best model. So print linear grid CV dot best underscore estimator underscore best score according to the metric we passed in refit. Print linear grid CV dot best underscore score underscore, and we get this. Then we find the optimal hyperparameters. So instead of writing the function for separate robust scalar and standard scalar data set, we create a function and we will call the function on separate data sets. Find the optimal hyperparameters from GridSearchCV. Definition find underscore linear underscore grid search CV of X train, Y train, and parameter grid. So these are the inputs. Define the classifier. Let linear grid CV equal grid search CV of linear regression open and close bracket, comma param underscore grid equal param grid, comma cross validation equal 5. Fit the best model from GridSearchCV. Linear grid CV dot fit of X the input train data set. Get the complete details of the best model. Print linear best estimator is. So linear grid CV dot best estimator. Best score according to the metric we passed in refit. Print linear best score is linear grid CV dot best underscore score underscore return linear grid CV. Call the GridSearchCV function. Let a linear grid CV SS equal find linear grid search CV of the standard scalar train set for features and the target and the param grid SS. So we get the best estimator has linear regression model copy underscore x equal false, comma end address for jobs equal 1, and the best score is 0.6516 and so on. Call the GridSearchCV function on robust scalar dataset. Linear GridCV rs equal find underscore linear underscore GridSearchCV of the robust scalar train features data and the target features data, data and the pram grid for the best robust scalar data from RandomizedSearchCV. Let's find the performance metrics based on these best parameters. Import time. From sklearn.metrics, we import mean underscore squared underscore error and mean underscore absolute underscore error. Fit and predict from the best model. Let model equal linear grid CV SS dot best estimator. Let time 0 equal time dot time open and close bracket. Model dot fit of standard scalar train dataset for features and the target. Let y predict equal model dot predict of standard scalar test set. Calculate root mean squared error. So let RMSE equal numpy dot square root of mean underscore squared underscore error of y test and y predict. Calculate the mean absolute error. Let MAE equal mean underscore absolute underscore error of y test and y predict. Let time underscore taken equal time dot time open and close bracket minus T0. Print root mean squared error equal curly braces dot format RMSE. Print mean absolute error equal curly braces dot format MAE. Print time taken equal curly braces dot format time taken. And we can see is the root mean squared error and the mean absolute error is quite high, and the time taken is 0.024 and so on seconds. Instead of repeating these functions on separate standard scalar and robust scalar dataset, let's create a function and we'll call the function on the data sets. So definition to calculate root mean squared error and mean absolute error. Definition: run underscore model of the input model comma the train data set and the test data set. Let T0 equal time dot time open and close bracket. Let model dot fit of the train data set. Let y predict equal model dot predict of x test data. Calculate root mean squared error. Let RMSE equal numpy dot square root of mean underscore squared underscore error of the test data set, y test and the y predict data set. Calculate the mean absolute error. Let MAE equal mean underscore absolute underscore error of the y test and the y predict data. Let time taken equal time dot time open and close bracket minus T0. Print root mean squared error equal curly braces dot format of RMSE. Print mean absolute error equal curly braces dot format MAE. Print time taken equal curly braces dot format time underscore taken. Retain model, RMSE, MAE and the time taken. Let's call the function on separate data set. Evaluate the linear regression model. Let model equal linear grid CV SS dot best underscore estimator underscore. array of model RMSE MAE time taken equal, we'll call the function run underscore model, and we will input model comma the train standard scalar feature data, the train data set for the response, and the test data set for standard scalar feature data, and the y-test value for the target. Create an array to store the scores for standard scalar feature data, feature values. Let all results SS equal square pair of square bracket that shows empty array. Save the results. Let all results SS dot append bracket and then the square bracket and linear regression comma linear grid CV SS dot best underscore score underscore and RMSE MAE time taken, and that gives quite high values. And printing the all results SS gives the model the best score value, the root mean square error, the mean absolute error, and the time taken. Calculate the linear regression model on the robust scalar dataset. Let model equal linear grid CV of rs dot best underscore estimator underscore array of model RMSE MAE time taken equal run underscore model of model X robust scalar train data set and the test set. Create an array to store the scores for robust scalar feature values. Let all results rs equal empty array. All results rs dot append bracket linear regression comma linear grid CV rs dot best underscore score underscore RMSE MAE and time taken. And let's print all results SS. We get linear regression model and we get the best score, RMSE, mean absolute error, and the time taken. It looks very similar to the standard scalar result, except the time taken, which is the difference of about 0.01 seconds. But rest of the values are almost the same.